Hi, my name is Matt Miller, and this is Lab 5 for Physics 2211, Choose Your Own Adventure. So in this lab, I will focus on observing an inelastic collision and how we might use observational data to estimate the coefficient of restitution between a dropped object and the surface. I'll use Tracker to observe the motion and then use GlowScript to conduct a computational model in which we can test different values to align the computational with the observed data. So I will first take a video of me dropping an object and observe that motion in Tracker through the full range of motion, and then take that and put it into GlowScript or extract the data and construct a computational model in which I will compare that with the observed model. So a little bit of background info. I'll be using Newton's second law to predict the motion of the object. You could have done it with the energy principle, but I chose to do it with Newton's second law. Another key factor in this lab will be the coefficient of restitution, which is the ratio of the final velocity of the initial velocity between the two objects after their collision. You can also find this by taking the square root of the ratio of the height of the ball at each time it's dropped. Some initial information is the ball's mass was 0.349 kilograms, and the initial position vector is given in meters, and the initial velocity vector was 0 meters per second. So here is the data from Tracker. You can see that I dropped the ball from an observed height and then tracked its motion as it fell and bounced multiple times. The x and y data is displayed on the right. So the fundamental principle at work here is Newton's second law, F equals ma, which F net is just going to equal the force of gravity in this situation because we'll be ignoring the drag force. The two change in position and change in velocities were both informed by Newton's second law and are defined by these equations. So for my code, I initialized it by setting the ball's mass equal to that of the ball I dropped. The ball's position vector and the ball's velocity vector are those of the initial values. And then the CR value, which we will get to more later in the lab, was found to be 0.75. And so in our while loop, what I did was I added an if statement to calculate the ball's bounce. And so each time the ball's velocity or ball's position equaled 0, which was when it hit the floor, I multiplied that by the CR value and negated the velocity. And so then we had the initial kinetic energy and initial gravitational energy. The F-grav equals the vector of the ball's mass times g, negative g. F net is just equal to F-grav, and then the ball's velocity and ball's position equations are dictated by Newton's second law. And so I coded it so that we could input a CSV file of the data extracted from Tracker, and we will compare that data with the computational model, which we will see in this slide. The blue ball is the computational model, and the red ball is the observed data extracted from Tracker. We imported the file and then let the code run, and you can see that as the balls bounce, they achieve a height that we can then analyze to calculate CR. I found CR to best fit at 0.75, and you can also fact check this by taking the square root of the height ratio of the first bounce to the second bounce, and so on. And you can see that the second bounce achieves about roughly the half the height of where it was dropped from. And the square root of 0.5 is equal to 0.707, which will then give you our CR value. So what does the COR say about our collision? The COR will depend on what two objects are interacting with one another and how they will store energy. When a soft object strikes a harder object, most of the energy available for the post-collision velocity will be stored in the soft object. The coefficient of restitution will depend on how efficient the soft object is in storing energy and compression without losing it to heat or plastic deformation. For example, a rubber ball will bounce better off concrete than a glass ball, but the coefficient of restitution of glass on glass is a lot higher than rubber on rubber because some of the energy in rubber is lost to heat when it is compressed. In conclusion, this lab is a simple way for us to understand an inelastic collision and make better judgments about how two objects will interact after a collision. Thanks.